Now in general, you can have beam elements which are under, of course, pure bending, but we also mostly encounter beam elements or elements that are under bending, show transverse displacement, but they also show axial displacement. That means you have an extra degree of freedom as compared to the pure bending element. These elements that show 3 degrees of freedom at each node, which include axial displacement, transverse displacement, and a rotation, are known as frames. So they are slightly different than the truss elements. However, you can use the basis of truss elements and beam elements together to form the frame elements. So frame element in general is actually a truss element combined with a pure bending beam. So if I have to draw the beam, the frame element, sorry about the bad drawing, then I will have at each node 3 degrees of freedom, which would look like this. So we will have UI1, UI2 and UI3, and same way UJ1, UJ2 and UJ3. Now how do we actually end up setting it up, right? Now we know that there are 2 paths that we can use. One is the truss element and the beam element. And for both these elements, we already have stiffness matrices that are set up. Let's call them KT and KB. Now we know that for a truss element which is lying in a 1D plane, we already derived the stiffness matrix, but we can do the same for a truss element that is also lying in a 3D plane. In a 2D plane. Now when we considered the truss element in a 2D plane, then we knew that there are 2 degrees of freedom that are acting at each node, which were UI1 and UI2. And in the global system, the UI1 was the only one which was filled in if the element was oriented in space in this direction, as shown in the figure over here. However, in this case, there are, instead of a total of 4 degrees of freedom, there are 6 degrees of freedom. So just as I showed you how to write down the truss element stiffness matrix for from a single degree of freedom to a 2 degree of freedom system, we can also expand it to a 3 degree of freedom system at every node. So let's start by writing KT here. Now we know that the standard form of KT, I'm going to write it here, is given as K 1 minus 1 minus 1 1, where there is only 1 degree of freedom. That means if there was only UI1 and UJ1, this would work perfectly fine. And then too, I do not want to use K here, but I want to use EA by L as the stiffness. Now if I'm going to expand this into a system for the KT where you have UI1, UI2, UI3, UJ1, UJ2 and UJ3, then I am looking at 1, 2, 3, 4, 5, 6 degree of freedom system. So my stiffness matrix therefore has to be a 6 by 6 square stiffness matrix. So I can write here a 6 by 6 stiffness matrix, where of course there are stiffnesses that are allotted only to UI1 and UJ1. That means I will have 1 and then I will have 0, 0, then I will have minus 1 and 0, 0. This will all be zeros because I do not have to have for every row. That means for UI1, UI2, UI3 I have nothing. Now with UJ1 I will have minus 1, 0, 0, 1, 0, 0, and then the same sparse zeros for the rest of the rows. So now I have a 6 by 6 matrix which defines the truss element. Then I can do the same thing for a beam element. Now for the beam element, I want to go back and show you the stiffness matrix that we had. This is also a 4 by 4 stiffness matrix because there were 4 degrees of freedom, and now we have 1 extra degree of freedom. Now it may be confusing for you now to see that, okay, here we use UI1, UI2, but those degrees of freedom notations have changed in the frame element. So what was UI1, UI2 has now become UI2, UI3 in this system if you look carefully. So transverse and rotation. So therefore now we can write K beam for an element. We are going to use the same UI1, UI2, UI3, UJ1, UJ2, UJ3 vector for displacement, and we are going to form a 6 by 6 stiffness matrix. Now we know that we do not have anything in the direction of UI1 and UJ1 for beam element contributions. That means these rows are going to be 0. And we have the standard stiffness matrix that was derived for beams, and we are going to copy these values into the correct locations. So now if I go back here, then we will have the value, we don't have anything for UI1, and we know the first column also represents, is going to be multiplied with UI1, so I can also fill in the first column with zeros, and so is the fourth column, so I also have fourth column as zeros, because this is corresponding to the first column, this is corresponding to the fourth column. Now I'm going to fill up the rest of the terms. So with UI2 I had 12, with UI3 I had 6L, and in the same way for the rest I can just fill up the rest of the terms for the corresponding degrees of freedom and stiffness. So these are the 2 stiffness matrices that I require for setting up a frame. Now this, if I basically want to find out what is the K of a frame, then I need to add the truss with the beam. Of course, there's an important term I forgot. EI by L cubed and EA by L needs to be multiplied here. So I need to get the frame, I need to have KT plus KB added up together to give you a stiffness matrix for the frame element, which has 3 degrees of freedom. So appropriate stiffnesses that are acting in the appropriate directions at the right degree of freedom in the element. So basically I'm going to do this just once because it might be easier for you to identify. The total stiffness matrix for an element is going to be given as EA by L, 0, 0, minus EA by L, 0, 0, 0, 12 EI by L cubed, 6 EI by L cubed, 0, minus 12 EI by L cubed, 6 EI by L cubed. And the rest can also be filled up in the exact same way. It's just a matter of getting the right equations through. Of course, you see that I have brought in the coefficients inside because they are not common for both the matrices. So it's important for us to also make sure that we have the right stiffnesses in the right locations. So these are for the 1 degree of freedom in the one direction, and then you have the rest for transverse and bending. So it's basically just copying the terms from each of the element matrices for truss and beam, so we can assemble it together to make a frame element. I would really encourage you to go about and set it up yourself, because this is something we may be using later in the examples or also in the exercises. So it would be very useful for you to learn how to set it up, probably make a little code out of it, a little program, so you don't have to keep doing it again and again, but so you can use the same matrix to make all other kinds of elements. Now of course this is for any beam element which is always lying in the global coordinate frame. Now, as we've already covered transformation, I'm not going to do that in details, but if I know the transformation matrix for any element, then I should be able to find out the global element stiffness matrix by multiplying it T transpose K T transpose, where T is the, T transpose KT, where T is the transformation matrix. Now, of course, the transformation matrix might be slightly different for a frame element than it was for a truss element. And the reason is that there are 6 degrees of freedom. So, of course, you need to make sure that you are not using the incorrect transformation matrix, and it has to be valid for these conditions. So, let's just look quickly at the transformation matrix in the next video.